So we are back with video 2.2, and in this video we're going to explore seasonality, how that affects climate, global wind patterns and how they affect climate, and then we are going to go back and look at other small topics that affect climate that we haven't had any place to talk about up to this point. After the last time, you understand the difference between weather and climate. You understand how the angle of the light that comes in affects the temperature at a given location. You understand how the greenhouse gases in the atmosphere warm the planet up over what it would otherwise be. And you know what the greenhouse gases are. And so now it is time to talk about seasons, because seasons play a big role in determining climates in a lot of areas. What is the reason for the seasons? I want you to think about that. You maybe switch off the video and see if you can think about an answer to that question. Okay, so you're back now? Good. If you said it's because the Earth is closer to the sun in the summer and farther away in the winter, well, congratulations, you guessed the very wrong answer that most people think is correct. Well, let's look at what's incorrect about that answer first. If true, both hemispheres would have summer at the same time because they'd both be closer to the sun at that time of year. The northern summer is the time of the southern winter and vice versa. So what's the real reason? Tilt. Tilt. The Earth is tilted at 23.5 degrees with respect to its axis. And here you can see our globe, and you can see that it is tilted. The Earth spins, and it spins on its axis. Here we have a diagram of the Earth as it travels around the sun. The first thing you need to note is that the Earth maintains its tilt relative to space, not relative to the sun. Can you see that here at December 21st, the northern hemisphere is tilted away from the sun and the southern hemisphere is tilted towards the sun? Here at June 21st, the northern hemisphere is tilted towards the sun and the southern hemisphere is tilted away from the sun. And that's because the 23.5 in this diagram is along this direction here, along this direction here, and at the so-called equinoxes, it's this direction. So let's take that all a little more slowly. The Earth's tilt of the 23.5 degrees means that each hemisphere is tilted toward the sun for about a quarter of the year. So here, June 21st, the northern hemisphere is tilted towards the sun, the southern away. Here, the 3-month period around December 21st, the northern hemisphere is tilted away from the sun, the southern hemisphere towards it. That leaves us half the year to explain, and during another quarter, the sun is approximately over all parts of the Earth in both the spring and the fall. So as we said, the northern hemisphere tilts towards the sun from March 21st to September 22nd and tilts away from the sun from September 22nd to March 20th. Because the Earth revolves around the sun but keeps its axis pointed in the same direction relative to space, there are other important latitude lines. One is the equator that bisects the globe into two hemispheres, northern and southern. The other significant part of it is that the sun is directly over the equator at 2 days a year, and those 2 days of the year are called the autumnal and the vernal, or the fall and the spring equinox. An equinox means equal night and equal day. At that time of year, when the sun is overhead, there is equal amount of night, 12 hours, equal amount of daylight, 12 hours, at all places on Earth. Now the tropics, the tropical lines, if we go back here, you may remember on most globes there is a dashed tropical line here, the Tropic of Cancer, and a dashed tropical line here, the Tropic of Capricorn, and they are the line which mark the farthest north or the farthest south that the sun is directly overhead in its annual cycle of moving up and down over the Earth. When the northern hemisphere is tilted towards the sun, like it is here in this picture you're seeing, on June 21st, the sun is directly over the Tropic of Cancer. And then on December 21st, when the southern hemisphere is tilted towards the sun, and you, the viewer, are the sun in this case, then the sun is directly over the Tropic of Cap. When it's directly over the Tropic of Capricorn. In the north, we call that the winter solstice, and in the south, it would be the summer solstice. And when it's directly over the Tropic of Cancer on June 21st, in the north, we call that the summer solstice, and we call that in the southern hemisphere the winter solstice. The summer solstice obviously is the longest day of the year in the north and the shortest day of the year in the south. Can you see why ancient peoples who were dependent on agriculture might have had a holiday to mark the winter solstice? It meant the end of creeping darkness and that soon the light would return and the ability to grow food with it. Make sense? Okay. What is the latitude of the tropics? You've probably been wondering that since I began this question. What is the latitude? If you guessed 23.5 degrees, the same as the tilt of the Earth, you should high five yourself. Let's go on and talk about the polar circles now. The polar circles are circles that occur in the far north. They run through central Alaska, northern Canada, Sweden, Norway, Finland, Russia. And then the southern circle circumscribes Antarctica, right? And what are the polar circles? They are the latitudes that are completely lit up and completely dark on the solstices. So here we have the northern summer solstice. On this day, this circle, you all in the class should be able to see all of this circle here. The sun sees it on June 21st, and that's all lit up. But this circle down here, this southern polar circle, the Antarctic circle, is completely dark on that day. And vice versa. When the northern hemisphere is pointed away on December 21st, well, right up here, this whole circle, the Arctic circle, is entirely dark for the day, and the Antarctic circle is entirely lit up. And the rest of the year, that circle of darkness is shrinking until it becomes entirely lit, and then it's expanding again to become entirely dark. What is the latitude of the polar circles? Give you a second to calculate it. Switch off the video if you want. If you guessed it's 90 minus 23.5, even if you didn't do the math, good on you, mate. Give yourself a high five. That would be 66.5 degrees north and 66.5 degrees south. Excellent now. So now we've got the reasons for the seasons. We understand seasonality. We understand light patterns on the globe. We understand when there's equal amounts of daylight on the globe, when there's darkness in the northern hemisphere, when there's lots of light in the northern hemisphere, how that affects temperature, etc. Now we want to do one last thing and talk about the fact that the atmosphere functions as a heat engine. So what the heck is a heat engine? A heat engine is an engine that uses combustion or some heat source, in this case there's no combustion, there's just a heat source, the sun, to create movement, to create kinetic energy. The most common heat engine we know is the gasoline automobile engine. We put some gasoline in the car, we burn it, it creates a drive force that moves the wheels and we get to school or go to California or something. Road trip. At the equator, where the sun is directly overhead, the most intense heating occurs. Warm air rises, and as warm air rises, it cools, and it splits to flow northward, as you can see happening here in this diagram. It rises, and it cools, and then it moves in both directions, north and south. The other thing that happens when air rises and cools, it's humid air, so you get a band of rain right there at this point where the sun is overhead. This is called the ITCZ, the Intertropical Convergence Zone. And we're going to see a picture of it on the next slide. It turns out that that air that has now risen up will move north and south, and it is dry and it is cooler, and as it moves north and south, and you can see here it is moving north and south, it all of a sudden sinks back down to Earth at about 30 degrees north and 30 degrees south latitude, right about here. And right about here, there's north latitude 30, south latitude. Now that air is very dry, and it sinks back to Earth, and then it flows in both directions away from the 30-degree latitude line. And since there's a lot of air being driven upward here, it flows back to that, okay? So we've set up this little cell here. Air moves along the surface back towards the equator as a south wind. Before I go on and talk about these cells, I just want to say the ITCZ is the major reason why tropical areas have a wet and a dry season. We've already established that the sun over the course of the year is on one day a year for the northern vernal equinox. It is over the equator, and then
it moves to north to about 23.5, and then it moves south back to the equator, and then back south to 23.5 south, and then back up to north. So on the vernal equinox, it's over the equator, then for the northern hemisphere, then on the summer solstice, it's over the 23.5 north latitude line, then on the autumnal equinox, it's over the equator again, and then at December 21st, the winter solstice, it is back over the 23.5 degrees south line. These atmospheric cells occur not only at the tropics, but also at higher latitudes. And you can see there's 1, 2, 3 north of the equator and 1, 2, 3 south of the equator. So these atmospheric cells in which air rises and flows and then falls back and flows along the surface occur in 3 places. And we're going to talk more about these cells. First, here's a picture of the intertropical convergence zone. Look at this. Here it is. Can you see this band of clouds? Here's a view from a satellite in space. And what an amazing thing. Here it is, that warm air rising. And there's some other effect that happens here, but there it is, the ITCZ. Yeah, you've seen it now, folks. Now, there's a quick refresher on wind direction that we have to do because wind direction's a little confusing. For most things, we specify the direction they are traveling. For example, if you sing the blues, I'm leaving tomorrow on that eastbound Sandy Fee. The eastbound Sandy Fee is heading east. That's if you sing the blues. If you're singing the weather, it's not true. An east wind is a wind that originates in the east and is actually heading west. A north wind is coming from the north but moving south. So wind is specified by the direction from which it originates. Why might this naming convention be? Well, take a second to think about it. Okay, you've thought about it? Perhaps it's because it gives an indication of its quality. A north wind in the northern hemisphere is a cold, dry wind. And so to say the wind is a north wind, you know what the temperatures that are going to follow are like and what the humidity that's going to follow is like and what the chances are for storms, etc., etc. Perhaps it's also because it's easiest to build a wind vane that points into the wind. And so since the vane points into the wind, we call it the north wind because that's the way the vane points. What I want to talk about next are these cells, these vertical cells of air movement that occur over the earth and create currents of air both at the surface and up high. So we said that the air sinks back down at about 30 degrees north and 30 degrees south latitude, and it spreads back out over the surface in both directions. Now think about the poles. At the poles, air is cooling there. That means that air is going to sink when it cools. It's going to be more dense air. Cool air is more dense because the molecules don't have as much kinetic energy, so they don't push against each other as much. Cool air is dense, and therefore it will tend to spread out. So we have this dynamic that at the equator, air is rising, and at the pole, air is sinking, and then we get these 3 cells. And notice their latitudes here. The boundaries are at 0, 30, 60, and then the end of the cells at 90. As a result of this, you get characteristic surface winds in these bands on the Earth. From 0 to 30, the winds are shown by the arrows in this diagram and are called the trade winds. From 30 to 60, the wind direction is shown by the arrows, and that's the direction the winds are headed, and they're westerlies. And then from 60 to 90, you have these winds that are heading to the east, and they're called the polar easterlies. If you've ever been to the Caribbean in the wintertime, you probably noticed that stiff northeast wind that you have most days, and those are the trade winds. So why does the wind blow? Well, let's think. When air molecules are packed tightly together, as when they are cold, this is high pressure. Think of the air in a tire. You're putting more and more air into your tire, your bicycle tire, your car tire, and therefore the air pressure goes up in them, and that's high pressure. When air molecules are not packed tightly together, as when they are heated, they expand. We call this low air pressure. And so now we can say that winds blow from areas of high pressure to areas of low pressure. Does that make sense? If you have densely packed air near areas with loosely packed air, Obviously, it's going to flow from high pressure to low pressure, just like any fluid, like water would do. Note the distribution of high pressure and low pressure areas on the globe. There's a low pressure area here at the equator because air is rising, and a high pressure area here at the pole because air is sinking. Here at the 30-degree mark, where cooler air is coming back down to Earth, there's high pressure. And here, where warmer air is rising up at 60 degrees, we have an area of low pressure. Each of these cells has an individual name, but in this course, we're going to refer to them all as Hadley cells. In truth, it's only the most tropical of the cells that is a Hadley cell. The effect of these cells is to take warm air from the equator and send it towards the pole, and to take cold air from the poles and send it toward the equator. And can you see that that is true? Here comes the warm air up here, and even though this is relatively cool compared to this, it's still relatively warm maybe compared to this air. Comes back down, warms up even more, goes back up, and then warm air goes and cools down here. So cold spreads out this way, and warmth spreads north. In other words, these cells make the Earth's temperature more uniform than it would be otherwise. Now talk about an ecosystem service. There is just an impressive ecosystem service right there. The three cells also have the effect of splitting the hemispheres roughly into 3 climatic regions. We're going to learn later that there are actually 5 climatic regions, but the first approximation would be what are the climates in each of these 3? From 0 to 30, we have tropical and subtropical climates. From 60 to 90, we find the coldest polar and subpolar climates, and from 30 to 60, temperate climates occur. Now we're going to have to modify that somewhat, but that's a rough approximation and a good starting approximation for climate. Now, where we live, where we have temperate climates, you can think that our weather is warring tropical and polar air masses. What does that mean? Think about the northern summer. Let's go back to the globe. At this time of year, the sun is directly over this part here, right? That means that the ITCZ is somewhere this far north. It's very close to this far north. That means the 3 northern cells have to get compressed this way. And the 3 southern cells spread out. Does that make sense to you? The northern cells get compressed and the southern cells get spread out. This allows tropical air to move farther north, while polar air is squashed into a smaller region. And this is why Washington, D.C. has hot, steamy summers. In the summer, we are living in tropical air. In the northern winter, when the sun is over the Tropic of Capricorn, these cells are spread out. The northern 3 cells are spread out, and the southern are crunched. That means this polar air up here can spread out a lot more. And this is why in our Washington, D.C. winter, we get cold, dry spells during the winter. And that polar air comes down, floods down. The transitional seasons are often a battleground where tropical and polar air masses collide with each other and create violent weather events. Not violent weather events, but violent weather events, such as thunderstorms and tornadoes. And that's it for today's talk. There's a lot in there. I hope you'll come to class with questions. Tomorrow we will be taking on, you notice that the winds, which looked like they should have either been directly north or directly south in the 3-cell model, in the Hadley cell model, are actually angled. And tomorrow we will take on the angle of the winds. We will take on how the winds affect ocean currents. We will look at some aspects of plastic pollution and ocean currents. And all this is prelude to next week when we'll be studying climate change. So until then, study hard.